often when you're trying to find something out, you can't make a direct measurement of the exact thing you want to calculate. But what you can do is a bunch of measurements that you can then combine into the thing you're actually interested in. So when you have uncertainties in the things that you measure, how do those uncertainties combine to give you an uncertainty in the final result that you're actually interested in? So suppose there's some quantity you want to know about, but it's a function of some other variable, which is the variable that you can measure. So the thing you can measure is called the raw data, and the thing you're trying to calculate is called the derived quantity. So my derived quantity is going to depend on the variable that I'm getting my raw data for. So supposing I measure a particular value for x, so I've got a particular value for that, of course I'm going to have some sort of uncertainty in that. So actually it's going to be some kind of bound there, and it's going to be somewhere in here. And this distance here is the delta x, our uncertainty in x. Now if we project that up to what y is going to be, obviously what we do is we'd say, well, that's the value of x that we measured, so this here must be the value of y that we derive. So because of our uncertainty in our raw data in x, we're also going to have some kind of uncertainty for our derived value of y. So just from this picture we can see that this here must be our uncertainty in y, in our derived quantity, and you can in fact derive that pictorially using graphing if you like. A more advanced way of doing exactly that process is to use calculus, but we're just going to work out a few rules of thumb for some very simple formulae that come up all the time. If we were doing this really carefully, we'd worry about the particular distribution of possibilities we'd have for our raw data, and we'd be able to convert that into a particular distribution for our possible results for our derived quantity. But we can get a good estimate by calculating this distance here. And that's just the difference between the values we would have got for y if we'd calculate it using the slightly higher version of x plus delta x, compared to if we'd used just the expected value of x that we'd measured. So let's look at a few cases. Firstly, let's look at a linear multiplier. In other words, what if y is just some multiple of x? Then if we use this formula here, if we expand out this bracket, we're going to get lambda times x and lambda times delta x. And the lambda x is going to cancel with this lambda x, and we're just going to be left with the other term. So that makes sense. If I take 10 times a measurement, then I should multiply the measurement by 10, but I should also amplify my uncertainty by 10 as well. So if I had an uncertainty of a centimeter across a meter stick, then if I was talking about 10 of those, I'd have 10 meters as my average, but I'd also have now 10 centimeters as my uncertainty. It's very common that we're actually making more than one measurement, and so a very common one would be something like addition. So there you might have two quantities that you're measuring, and you're just adding them together. So in that case, we can follow exactly the same process. Well, now we've allowed our derived quantity to depend on more than one variable. And that means that when we're estimating our uncertainty, we would have both this variable going to an extreme value and that value going to an extreme value. And so what we've done down here is we've said it's just addition, so I'm going to have a going to a plus delta a, and we're going to have b going to b plus delta b, and we're just taking away our average there. And if we expand out the brackets, the a cancels with the minus a, and the b cancels with the minus b, and we just get these two things added together. So for addition, you add the uncertainties.